We're now looking at the integral of a vector function. Assume we have an arbitrary vector function that's given, and that vector function has the parametric equations f at t, g at t, and h at t. And let's also assume that each of these parametric equations are continuous functions over some given interval. The integral of a vector function can be also written as the integral of the vector function where we have f at t, g at t, and h at t written in our pointy bracket notation. And in order to calculate the integral of this vector function, we quite literally are going to be taking the integral of each of the individual components. So just like taking the derivative of a vector function, we differentiate each of the components. To calculate the integral of a vector function, we integrate each of the components. So let's look at the antiderivative of f at t and let that antiderivative be cap f, so that if we were to differentiate cap f, we would get the parametric equation f at t. Similarly, let's let the antiderivative of g of t be cap g at t, meaning that if we were to differentiate g at t, we would get the parametric equation g at t. And let's let the antiderivative of h at t be cap h at t, so that its derivative is the parametric equation h at t. Now, if we were to take the antiderivative of the parametric equation f at t, we would get the antiderivative. And when we're looking at an indefinite integral, of course, that we would add on the possibility that a constant value could be part of that function. Now, since we'll be doing that a couple times, let's call this C1. And the antiderivative of g of t is cap g at t, having the potential for another constant. Let's call this C2. And the antiderivative of our h parametric equation would be cap h, and again holding space for the possibility of another constant down here. So when we calculate the antiderivative of a vector function, what we'll get is another vector function that is the antiderivative of the original vector function. And that antiderivative is going to be f at t plus c1, g at t plus c2, h at t plus c3, which is a vector function that can be decomposed into, let's call it f at t, g at t, h at t, plus the constant vector c1, c2, c3. So let's do a little better with our notation here and try to simplify this. Let's let cap r vector function be equal to this antiderivative vector function, where the components are all the antiderivatives of the parametric functions from the original, and let's let cap c vector be the constant vector c1, c2, c3. Now that's going to give us a more compact notation when we refer to the integral of the vector function. It's going to end up being the antiderivative of that vector function, or the antiderivative of each of the components, plus some constant vector. And this is what we get when we're calculating an indefinite integral. Now, if we were calculating a definite integral where we have limits of integration that are being imposed, then similarly, we're going to be calculating the integral of all of the individual components, also applying those limits of integration to each of the parametric equations. The fundamental theorem of calculus from single variable calculus is going to also extend into vector functions. So again, letting cap r be the antiderivative vector function for lowercase r, where if we were to differentiate cap r, we get lowercase r as the vector function. And if we're calculating the definite integral of r of t evaluated at the limits taken from the value a to the value b, that definite integral is going to be calculated by looking at the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. This is similar to what we saw in single variable calculus, and it also applies to vector functions.